In this video 8, I will introduce the guarded successor logic, which is a family of logics, but as we shall see, when we deal with the Atomless Boolean Algebra, it becomes very powerful. And this is a novel temporal logic and software specification language, but maybe before we say what it's good for and what are the novel stuff about it, let's first just jump right to the matter. So first, we define time-compatible structure, or in short, a TC structure. So given some domain, D, a TC structure over D will have as its domain D star. This is clean star. So it is the set of all finite strings with the alphabet from D. Now let me just call it, this is a finite time TC structure, while an infinite time TC structure is going to have as its domain D to the omega, so it's all infinite strings with alphabet from D. As we shall see, our derivation will not make much difference between finite and infinite. Are going to behave the same, mostly due to Löwenheim's-Kollen. As long as, of course, you are in the realm of first-order logic, which we will mostly be in indeed. Now, that's not the whole definition. So it is, we said, what is the domain of a TC structure? Now, is also equipped with a function. So we can look at it as a unary function over the domain of the structure, although it can be a k-ary function. It can take multiple sequences and return multiple sequences, as we will comment later. But the most important thing is that this function is prefix preserving. So if a sequence S1 is a strict prefix, so it's not equal to S2, is a strict prefix of S2, then FS1 is a strict prefix of S2. Now, first, note that this models programs. If the input of the function of this f is the sequence of inputs to the program, then D is a sequence of outputs to the program. And the time compatibility requirement, prefix preserving, I will refer to prefix preserving as interchangeably as being time compatible, simply means that current output does not depend on future input, like in any program. Right? So it's not an arbitrary function from sequence to sequence, but you can produce the output only based on the input you saw so far, because you still didn't see the next input. And therefore, specifically, time-compatible or prefix-preserving structure quite generally models programs. Another comment about what I said before, so this f may take n sequences and return k sequences, and everything I'm going to say about time-compatible structures and the guarded successor, I will speak about mostly about taking one sequence and returning one sequence, but it will all apply mutatis mutandis to taking several sequences and returning several sequences. Another note, important note, is that this extends to trees. Everything we are going to say about time-compatible structures, and most importantly about the logic-guarded successor, can work not only with strings, but also with trees, simply by considering multiple successor relations. So far, we didn't see a successor relation yet, but it will come. Now, we define the notion of bounded lookback. So a TC structure is of a bounded lookback of length k. I have to do another modification first. So this f, written like this, it can also be written as f takes a function from the natural numbers to the domain and returns such a function, because f takes a sequence and returns a sequence. Now a sequence is a function from the natural numbers to the alphabet. If it is a finite sequence, then you can consider some symbol that denotes nothing, and then it repeats this nothing from one point on. But note that even this is too general, because in this definition, we do not assume time compatibility. But if f is time compatible, then can be typed as like this. You give me a point in time, and I give you a function from specific input to specific output. Now, taking this typing, so at each point in time, at each natural number, we get a function from d to d. So now we can go back to define bounded loopback. This structure is of bounded loopback if fn for each n depends only on f n minus 1 and so on, and f n minus k. So the intuition is that it looks at the history only k steps back, but of course it might accumulate stuff over something which is greater than k. Let's take a numerical example that fn equals fn minus 1 plus 1. So here the lookback is only of 1. So this k, in this case, is 1. But depends where you start the sequence, it's going to influence all time steps. Now, one important point about functions of bounded lookback is that in its type, you don't need to write the natural numbers. So this n is going to disappear, and here you can write it as something like this. So you take k elements, and you return one element. And as you can already see in this example, also it does not depend on time. It's not that we had plus n here, right? You could at the same time write just a recurrence relation, xn equals xn minus 1 plus 1. And indeed, I said the word recurrence relation, as is already apparent from here. Indeed, we are going to speak a lot about recurrence relations. Now, this is not enough. Just like in this recurrence relation, you need to specify the starting point. You need to specify f1 equal 5, let's say. So a function of bounded loop can be typed as a pair of functions, one of type this, and another of type, this thing means all natural numbers from 1 to k of this type. Also, here you have, at each point you have a function. Here you have a constant, because here in this example, I didn't take into account that the program have inputs. Indeed, if you have only outputs, you speak only about a sequence and not about functions between sequences, then you can assume that the input sequence is fixed. Indeed, in this logic, you can specify, obviously, not only prefix-preserving functions between sequences, but also simply sequences. So this second function is going to define the initial condition for the recurrence relations. Now, any formula in virtually any logic with 2k plus 2 free variables can be seen as defining a set of bounded loopback of size k structures. So for example, if we have some formula that takes the input at time n, connects it with the output at time n, and also connects it with the input time n minus 1, and the output at time n minus 1, and so on, until xn minus k, and yn minus k. This defines a set of structures, a set of time compatible structures. Here we took into account only this part. We didn't take into account the initial conditions, but you could, of course, put constants here. I'm going to put only for the outputs, as you shall see later why. So here you can also define some initial conditions. And now the main question is, given such a formula, can we decide satisfiability? Or maybe I had to say, I didn't say how this formula defines a set of structures. Well, it's obvious. You should see this as having the infinite quantifier prefix for all input at time 1 exists output at time 1, such that for all input at time 2 exists output at time 2, and so on. And note that there are infinitely many quantifier alternations here, and the quantifier structure defines time compatibility. If we didn't want to be time compatible and speak of some arbitrary function between sequences, then it would look like this. But here, y1, the output at time 1 depends on the input at time 2, which is of course not time compatible. And therefore we get this quantifier prefix. Now, for satisfiability, namely whether exists a time compatible structure that admits this formula. So in other words, how to append this infinite quantifier prefix and get an answer. So let's start with a simple example, with a simple case. So given, let's say, phi that takes the input at time n and has a look back of inputs only one step before, and the output at time n, define phi n to be phi n that has a free variable called the x1, to be a formula that says exists a TC structure of length n. Length n means the number of time points, so it's a function from sequences of length n to sequences of length n, starting with x1. So how does this recurrence relation look like? Exists a sequence of time 2 that starts with x1, would mean that for all y2 exist x1, x2, such that phi x1, x2, x1, y2. Now, exists a sequence of length n that starts with x1. Well, so first there should be a sequence of length n minus 1 that starts with x2. So this 2 comes here, and here will come number 3, and here will come number 3. And we need to conjunct to what happens at the beginning. So x1, x2, y2 should also be connected. And now how is it quantified? Well, exactly like this. Yes, so this is going to define that exists a sequence of length n starting with x1. Now, this thing has, of course, a free variable. So to get a final answer, I will need at each step to quantify this variable. And then if it is satisfiable, then exists a sequence of length n. Now, when can I get the fixed point of this recurrence relation? Well, for one thing, please first note that due to monotonicity, it always has a fixed point, but maybe at infinity. Because if exists a string of length n, then of course exists an TC structure of smaller length. Therefore, even though we have a quantifier alternation and conjunction here, the conjunction is okay, but the existential quantifiers are the main problem to see this monotonicity, even though it is still monotonic by construction. Now, to find the fixed point of this recurrence relation, if the language is the language of atomless Boolean algebras, so the connection between the x's and the y's here are given in the language of atomless Boolean algebras, then we already saw that when we spoke about weakly omega categorical theories in video 5, and I gave this example, and this example is indeed about time-compatible structures. We saw how we can unfold this recurrence relation and get an answer in finite time. So one thing we get here is temporal logic over infinite alphabet that comes not only with equality, but with a rich theory, relatively rich theory of atomless Boolean algebra. Moreover, it is decidable whether for all input exists a time-compatible output. And these two properties together, I'm not aware of other temporal logic that allows you to do so. There is one temporal logic over infinite alphabet, which is the two-variable fragment, certain kind of the two-variable fragment, discovered by Boyanchik, where he showed that with equality, we still maintain decidability. However, here it's not only equality. And moreover, you can prove that for all input exists a time-compatible output. Two major decidable fragments of first-order logic are, as you probably know very well, are the two-variable fragment and the guarded fragment. As I mentioned before, Nikolai Boyanchik discovered the two-variable fragment, a certain kind of two-variable fragment that has decidable temporal logic over infinite domain. And as promised, what I'm showing you here has to do with guarded successor. Now, it is not exactly guarded in the sense of the guarded fragment. There are several senses of guardedness in the guarded fragment. There is the guarded, there is the loosely guarded, clearly guarded, and so on. None of which is the kind of guardedness that we are going to speak about here. I will show you exactly what I mean. For example, this formula can be written as for all nk. Now nk are of the sort of natural number. If n is the successor of k, then now I need a function symbol. So this is a function from the natural numbers to domain elements that defines, of course, a sequence. So as we said before, this thing, a function from n to d, is a sequence. And that's what we have here. We have the sequence of inputs and the sequence of outputs. So we can see very easily how any formula with three variables of this form that defines a bound and look-back set of structures can be written in this guarded fragment. In this guarded successor, we see that guardedness applies only to successor. Now, what if we had also xn minus 2? Okay, I made a mistake here. I had to use k. Okay. Yes, I don't have arithmetic. I have to use k. Well, I could write it like this with arithmetic with n minus 1, and it would be equivalent to using directly the successor. But what if I wanted also another step back? Then I could write and s km. Still, we can decide this by the same means that we saw before. So the precise definition of guard in this guarded successor logic, so successor relations appear only as guards, and such that the relative position of all position variables, relative position, okay, is fully determined. So the structure of the guard should tell me what is the distance between each two variables, a number, that m is 3 steps from k or something like this. Now, of course, this is not the full guarded fragment, but we will support the full guarded fragment. And What do I mean by full guarded? Yes, it's not a full guarded fragment. What I mean is if you have existential, then the guarded formula looks like this. But first, let me show you quantifier collapse. If you have for all n exist k such that if n is successor of k, then all the rest. By the way, this is also for richer guard because this conjunction I can also write like this. Like this. So this for all exist is the same as for all, because each number has only one successor. So this is nothing but for all. So any quantifier prefix of successors appearing over, you quantify over successors appearing only in guards, where the successors appearing only in guards, not the quantifiers, can be collapsed to no alternation, namely only for all or only exist. Now, I showed you how to decide a formula with only for all. To handle the rest, I will show you how to handle Boolean combinations, conjunction, negation, and disjunction. Now, if you look at the free variable formulation, which is this, you can, of course, conjunct, disjunct, and negate formulas with free variables, but it is not the same as union, intersection, and complementation of the sets of time-compatible models that they define. It is the same only for conjunction, but it is not the same for disjunction and negation. To take as an example, if I have, let's say, a formula that says xn equals 0 or xn equal 1. So it says that there are no inputs, only outputs. The outputs are either 0 or 1. It is very different than saying either for all n xn equals 0. By the way, as you can see, if you quantify over a single position variable, then you are already guarded. You don't need a successor. You don't need the guarded successor relation. So this thing is very different than this thing. This thing says either everything is 0 or everything is 1. So we have two Boolean algebras here. One with respect to the open formulas and one with respect to the sets of models. Now, to decide the disjunction, existence of two formulas with respect to sets of models, okay, that's very easy. I simply check if one of them is satisfiable. So assume a Boolean combination of sets of models, write it in DNF. Now decide emptiness for each DNF clause. Conjunctions are well behaved. So if we take this example, so let's say here, so the conjunction, for the conjunction to not be empty, let's say this is strictly greater than 0, and this is strictly smaller than 1, and here we have conjunction. This is the same as this. So to conjunct the sets of time-compatible models, it's the same as conjuncting the formulas with free variables. So if you have a DNF clause, so each DNF clause has one positive and multiple negatives. It looks like this, yes, phi and the complement as sets of models of each CI. Now, to decide emptiness of this, that's also possible. You can see this in the TABA document. That's a little bit involved recurrence relation. You simply encode recurrence relation that says up to length n, p held, and certain subset of the psi's didn't hold. They should not hold because they are negated. And the rest that did hold, they should fail right now. Yeah, so you can see in Taba the full formulation of a decision procedure for this. So we can see that this is decidable also under Boolean combination of sets of models. Now let's see some correspondence with the automata and transducers. So automata, no output, yes. Transducers with output, all with a finite alphabet. It is easy to see that they correspond to bounded loopback over finite domain. Automata as formulated, they don't have a loopback at all, but you can always simulate bounded loopback by exponentially increasing the alphabet size, and in turn also your automaton size. So we can see that this formulation can reduces to automata in the finite case, but in the infinite case, like in any weakly omega categorical theory, like in the theory of Boolean algebra, we get a certain kind of automata over infinite alphabet that can probably be expressed using open formulas, as we saw, formulas with free variables. In the finite case, you can also explain this by means of weakly omega categorical theory, because if you have a theory of a finite alphabet with equality, which is what automatas deal with, then of course you're weakly omega categorical, because there are only finitely many formulas with prescribed set of free variables and prescribed sets of constants, as quantifiers can be eliminated very easily, and even quantifier-free formulas, you have only finitely many of those under this condition. So it all falls under this framework of bounded loopback structures. Let's consider a fourth law of robotics. You are probably familiar with the three laws of robotics by Asimov. Let's imagine a fourth law that says any future software update to the robot should admit the laws of robotics, because you don't want to plug in a USB stick to your robot and install a software update and it suddenly starts killing people, right? You don't want that. You want the robot to reject the update if certain conditions are not met. Now, the robot and the update are written in the same language, because otherwise you are not gonna use many languages, one per each update. Yeah, that's not gonna work. You need the robot and the update to be written in the same language. So it has to be a language that can take as input a statement in the same language, yet the language that the robot is programmed at receives the software update as inputs in the same language and checks satisfiability against other such sentences. So the robot is programmed to take another program, conjunct it. What does it mean to conjunct program? Okay, we can conjunct specs. Okay, so it takes a spec, conjuncts it with the laws of robotics, and checks if this is empty, if there is a model. If it's non-empty, then there is a model. If it's empty, then it rejects the update. Of course, you should say differently. You should really speak about entailment, and entailment is conjuncting with the negation and checking for emptiness. Yeah, but that's aside the point. The main point is there is no language that can do this, other than a guarded successor is the first language that is capable of doing so, because it can speak about its own sentences, which is using the same trick as NSO that we spoke about. So these inputs and outputs, this X and Y, and they can come from atomless Boolean algebra. Which atomless Boolean algebra? Well, the one of guarded successor formulas. And by the way, you can add the same language, speak of product algebra, and have a many sorted theory of Boolean algebra. So you can speak about multiple Boolean algebras at once. One of them will be the Boolean algebra of guarded successor formulas. So not only this language, which we will call, let's say, the tau language, the tau equals, roughly speaking, NSO plus a guarded successor. It's more than that, but let's say roughly speaking. So not only the Tau language can speak of its own formulas, but one, it is also rich enough to express software. I'm not aware of an example of real-life software that cannot be expressed in guarded successor. If you have an idea, please tell me. And inputs, outputs of this software are nothing but sentences in various logics, including the Tau language. So the Tau language is a specification language that specifies program, and those program takes as input and output specifications. It's a specification of time-compatible functions between specifications. And then you can finally implement the fourth law of robotics, and I hope I convinced you that this setting that we can see here for the first time is absolutely crucial for AI safety. You want the AI to never break certain conditions, but you're not going to invent infinitely many languages just to start speaking with your AI. It's not going to work. You need a trick of this form. Now, we said that the language can speak about multiple Boolean algebras at once. So which Boolean algebras typically should occur that we intend to implement in the Tau language? So for one thing, of course, the Boolean algebra of Tau formulas themselves. Second, fixed finite Boolean algebras. Yes, so let's say the Boolean algebra of bit strings of length 64. And then you can do more or less a standard bitwise computations. The whole idea here can be seen as follows. The common model of computation is when you manipulate bits 0 and 1, bits come from the smallest Boolean algebra, the two-element Boolean algebra. But we say, let's extend this model of computation that these bits come from infinite Boolean algebra, in particular atomless Boolean algebra. Another Boolean algebra, or in other words, we call it also base logic of choice, is the two-variable fragment with counting. And this is not the temporal two-variable fragment I mentioned before. This is the standard two-variable fragment with counting. The reason we chose this logic is because it covers many description logics and is therefore very useful for knowledge representation. Now, to make programming in the Tau language even easier, you can see on Taba that there is a definition of tables in the Tau language. It's a syntactic sugar, but it allows you to define tables similar to relational database and do basically all relational algebra over them. They come with some bound on the size. You encoded their size in bits. So here you use the fixed finite Boolean algebras and certain kind of simple Boolean functions that allow you to have tables of fixed bit width index, but other columns can come from even infinite atomless Boolean algebra. It's not full relational algebra in theory, but in practice you get basically all what you need. And of course, with any Boolean algebra you choose, you get for free infinitely many more Boolean algebras, which are the Boolean algebras of Boolean functions and simple Boolean functions. And of course, all equipped with additional conservative extensions to the theory of Boolean algebra as described in Taba PDF. Yes, so I guess we finished. I took you almost from scratch until the logic guarded successor and the Tau language. Thank you very much for listening.